So our first speaker today is Yinan Wang, and Yinan will tell us about elliptic Calabi-Yau manifolds with the largest h11. Take it away, Yinan.
Okay. So first, I'm going to thank Cody and John for inviting me to give a talk at this nice string field series. So today, I'm going to talk about the elliptic Calabi-Yau manifold, the largest Hodge number h11, which is based on two of my recent works. The first one is the one early last year about the Calabi-Yau fourfold with maximal h11 in the 4D F-theory framework. And the second one is a more recent one with Jiahua Tian on elliptic Calabi-Yau fivefolds and its relevance in the 2D 0,2 F-theory landscape. So first, I'm going to present my mathematical motivation. So what is a precise mathematical question we want to ask? So given any compact, irreducible, complex d-dimensional Calabi-Yau manifold XD, where d is greater or equal than 3, then we want to know what is the maximum possible value of the h11 of this XD. So we define this particular positive integer to be big HD. Now, physically, this particular Calabi-Yau manifold is kind of interesting because if we consider various kind of string or empty compactification on this XD with maximum h11, then you can give rise to the currently known largest number of certain type of fields coupled to supergravity in a specific dimension, and with a specific supercharges. For example, if we consider the Calabi-Yau threefold with a maximum h11, then if we put an 11-dimensional M theory on it, that will give rise to the largest number of vector multiplets in the 5D n-1 supergravity landscape. Similarly, if we actually use the same Calabi-Yau threefold, but with the elliptic structure in mind, then we can study the F-theory on this elliptic Calabi-Yau threefold with maximum h11 as well. So that will give rise to the largest number of both tensor and vector multiplets in the currently known 61,0 supergravity landscape. And also similarly, if we use a Calabi-Yau fourfold instead, and so we can have the largest number of axion scalars and vector multiplets in the 4D n-1 supergravity landscape as well. So of course, if we want to answer this mathematical question, it's extremely hard. So we don't really have an existing tool to kind of approach this question yet. Nonetheless, if you restrict ourselves to a subset of Calabi-Yau manifold, so that's a ones with an elliptic structure, then this question is a little bit simplified, because very recently, it is conjectured that most of the Calabi-Yau manifold with a moderately large h11 has this elliptic structure. For the Calabi-Yau threefold case, there have been a few works on this. So in the particular subset for continuous section Calabi-Yau, the CC subset, people have shown that over 99% of them has an elliptic structure. And then for a much larger subset, that's a Batiev construction as a Calabi-Yau hypersurface in a reflexive polytope. There's a recent paper by Yinan Wang and Watty Taylor, which really shows that all these Calabi-Yau threefold in this class with either h11 or h21 greater or equal than a certain value, so they always has an elliptic vibration structure. And also, for a smaller h11, they also show that there's an approximate formula for the fraction of polytopes without a toric vibration structure. So that scales exponentially like 2 to the 5 minus h11. So basically, if you take this h11 of x3 to be like around 20, then the fraction is extremely small already. So that all suggests that for most of Calabi-Yau with a kind of large h11, they're obviously elliptic. So one may also ask the following question, whether the maximal h11 for elliptic Calabi-Yau is equal to the maximum number of h11 for the general Calabi-Yau. So we have lots of hints such that this statement is actually true. So of course, it's also very hard to rigorously prove that. And also, despite the progress in the Calabi-Yau threefold case, not much has been known about the Calabi-Yau fourfold or higher dimensional cases. And nonetheless, if you just think about the absolute applications, if this Calabi-Yau manifold with large h11 has an EDP structure that we can explicitly write down, then that will have some very interesting physical applications. So now I'm going to present the state-of-art records on the maximal h11 in various different dimensions. So most generally, in 1997, there's a paper by Claim, Lian, Rong, and Yau, where they constructed an infinite sequence of Calabi-Yau manifold that give rise to the currently known extremal Hodge number. So the construction is as follows. First, we define a sequence of integers, start with m0 equal to 1, and then the next number can be computed from the value of the previous one, like this mk plus 1 equal to mk times mk plus 1. So basically, one can easily compute the next follow a few mi's, like m1 equal to 2, m2 equal to 6, and 42, and so on. Then we define a reflective polytope with d plus 1 dimensions that are associated to a weighted projective space whose weights are computed using these MIs, like this. It turns out that for any value of d, this polytope is always reflexive, so we can just define the Calabi-Yau hypersurface in it. Another very interesting feature of this polytope is that after rotation, this ambient space, you have the following form of vertices, which means very natural P231 vibration structure over a d-1 dimensional toric base. Then, because of this, the Calabi-Yau hypersurface is an elliptic vibration over a toric base. It could be d-1 star. And for this particular Calabi-Yau, if you have the extremal hd-1, comma 1. So here I list the first few examples. Where in the Calabi-Yau threefold case, that gives rise to the one with the maximum h21, that's 491. And for the fourfold case, that gives rise to a max h31. And then for the fivefold case, that gives rise to the maximal h41. And so those numbers are computed in your recent paper as well. So in fact, these Hodge numbers are kind of simple to compute just by applying the Landau-Ginsburg method in Bafa's old paper. So there's nothing hard about this. So now, as I said, this polytope is reflexive, which means that we can just simply take the dual polytope of it. And then the Calabi-Yau hypersurface inside this dual polytope will give rise to the xd of the Calabi-Yau d-fold with the extremal h11 from the mirror symmetry. Okay. Then from this class of examples, we get our currently state-of-art records of the maximum value of h11 in the Calabi-Yau manifold in any dimensions like this. So as you can see, these numbers grow exponentially, like approximately the next one is the square of the previous one times the order 1 number. And then another very interesting fact and observation is that for this one with a maximum h11, its ambient space is delta d plus 1 can also be rotated into the form of a P231 vibration as well. Then this basically means that the Calabi-Yau d-fold with maximum h11 is always an elliptic vibration over another base manifold, B d-1. Another very nice fact is that if we want to compute the F3 gauge group on each toric divisor, then there's a nice trick because we know that all the monomials in the Tate model, they correspond to the lattice point in its dual polytope, and the dual polytope is already known. Then we can basically simply resolve the gauge group over each toric divisor by computing the order vanishing of like the Tate coefficients. So this is a general result in general dimensions. And so a very interesting fact is just that the EDP vibration structure will always exist in any dimensions. So now I'm gonna present the full details of the Calabi-Yau threefold, fourfold, and fivefolds. For the Calabi-Yau threefold with the largest h11, so this one has a h1 equal to 491. So this was constructed by Dave Morrison and Wattie Taylor in 2012 as a generic EDP vibration over 2D base B2. The construction of this B2 is like this. So we start with a toric base here. So on a toric twofold, the toric curve are organized like in a circle. So here each number means the self-intersection number of a toric curve. And the slash denotes the Z sequence of curve that appears in the tensor branch of a EA conformal matter. Then from this toric base, because there are still two -11 curves, so that gives rise to a non-minimal locus in the 60F theory. And we need to blow up these 2-1 and 2-11 curves at generic point to remove this coordination 246 point to make the final EDP vibration fully flat. And in the end, actually, this base B2 is no longer toric. Physically, in the F3 application, so this particular model will give rise to the largest number of tensor multiplet and also the rank of gauge group in the known 61,0 landscape. Of course, it would be extremely interesting if one can kind of prove this physically, but up to now, I think the swampland technique is still not enough to do this. All right, so this is a review of the Calabi-Yau threefold case. So what about the Calabi-Yau fourfold? For this case, I constructed the explicit structure of this Calabi-Yau fourfold as a generic vibration over a base threefold in my paper last year. The construction has several steps. So first, we construct a non-compact toric threefold we call BE8, given by the following 3D polytope. The particular reason for choosing this toric threefold is that we want to put an EA gauge group on each of them, because these are particular the divisors that give rise to the EA gauge group in the Farian geometry. Then if you start with this, we triangulate it and we tune E8 on each of integral point on this polytope. As a consequence, there are lots of collision between like 3 E8 or 2 E8s, or there are lots of coordination 3 or coordination 2 non-minimal loci on the base. Then we need to blow up all those non-minimal loci in the following way. So here I present a picture where there's a big triangle, 3 EAs, and after a bunch of blow-ups, you add more exceptional divisors in it, and in the end, the whole thing is just give rise to a flat vibration. Besides the toric blow-ups, you also need to blow up a number of non-toric coordination 246 loci, which correspond to curves on the EA divisors. And finally, you need to add like 2 more rays into the whole thing to make the whole base compact. So you get the final base threefold. Okay. So as a consequence, this particular geometric model will give rise to the largest geometric gauge group as a huge product of the EA type 4, G2, and SU2s, and also the largest number of axions in the whole 4D inclined landscape. The number of axions just equal to the h11, the B3 plus 1, at the order of 100,000. And as a conclusion of this part, I'm also going to briefly comment on the model-stabilization of this particular model. So recently, there's a very nice work by Bina, Blabach, Grana, and Lust, who also give a talk at this series, I think. which they basically argue that for the Calabi-Yau fourfold is a moderately large h11 comparing to the h11, and because the number of choice of the G4 flux is very limited, so not all of the complex structure moduli can be stabilized. Nonetheless, in this particular regime with large h11, and then the Euler characteristic of the x4 over 24 is still much bigger than the h31 of the x4. And this basically suggests that the complex structure moduli can be fully stabilized on this geometry. Nonetheless, in this case, because the h11 is very large, I may wonder whether we can stabilize all the Kähler moduli. So there's also a recent work by Jim Halvorson, Professor Fabian Ruhle, and Jiahua Tian, which shows that if on a base threefold, if the divisor comes from blowups, then this Kähler moduli can be stabilized. And this is exactly the case of our geometry here. Although this, the full model stabilization of this model is still not proven yet, and I also think another very interesting question is to ask how do we construct the models with a standard model sector in this particular regime of large h11, such that all the moduli can be stabilized. I think that's also a very interesting question to be answered in the future. All right, so this is a Calabi-Yau fourfold case. Let's go into our more recent work on the Calabi-Yau fivefold and its relevance in the 2D F-theory. For the 2D F-theory, in the past a few years, there have been serious works by Timo Weiga and Sakura Shafranamiki, and Craig Lowry and Feng Junxu, where they established the framework of 2D F-theory on Elliptic Calabi-Yau fivefold. So the physical story is kind of analogous to the higher dimensional cases, where one can start with an M3 on the resolved Calabi-Yau fivefold to get a 1D equal to zero quantum mechanics that's worked out by Haupt, Landry Lucas, and Stanley more than 10 years ago, and then just perform the M3F3 duality to uplift it to 2 dimensions. So one may also wonder, why do we study the 2-dimensional cases? Well, there are 2 nice reasons. The first one is similar to the 60 case, and there's a pure gravitational anomaly in 2 dimensions that can be checked nicely. And the second reason is that there's a rich field of the 2D field series like GLSMs. So maybe the field series and supergravity series engineered in the 2D F3 approach can be related to this existing literature as well. So now I'm gonna briefly list the super multiplet structure of the 2D 0,2 theory that includes a vector multiplet, a chiral multiplet, a new so-called Fermi multiplet that has an opposite chirality as a chiral multiplet, and also a 2D tensor multiplet that only basically has a scalar field here. And finally, the unique supergravity multiplet in the theory with gravity. Now, basically, the important thing is the chirality over here, which is pretty relevant in the discussion of the gravitational anomaly cancellation later. So in this case, we can also compute the number of vector multiplets, so the rank of gauge groups, using this Tate Schroeder-Wazir formula. It's using h11 of the Calabi-Yau fivefold and subtract the h1 of the base fourfold. But that's also completely parallel to the the 4D and 6D F theory. So it's not super new. Before I'm going to go into the particular detail of the gravitational anomaly cancellation, I'm going to just first present our newly worked out Calabi-Yau fivefold with the largest h11. So this h11 is pretty cute, has over 1 billion. And so it's also constructed as a generic elliptic vibration over a base fourfold in the following steps. So this is actually just quite parallel to the Calabi-Yau fourfold case. So step 1 is we start with like a non-compact toric fourfold. We triangulate it between an E8 on each lattice point, And then we blow up all the non-minimal collisions that also include the new case of the collision of 4 E8s. So the resolution is like this on the base. And then we blow up all the non-toric, non-minimal loci on the E8 divisors, and finally make it compact. So as a consequence, we computed the h11 of the base and also the full geometric gauge group, and if you sum them up, sum all the gauge rank up, then that matches the h11 of the x5. So everything is cross-checked, basically. Then besides this particular Calabi-Yau fivefold, we also studied a list of a very small list of Calabi-Yau fivefold hypersurfaces as a reflexive weighted projective space, which has an obvious P231 vibration structure and a low degree. So this is actually the first attempt to like systematically study a number of Elliptic Calabi-Yau fivefold in the literature. So in this particular subclass, there are only 140 cases, not too many of them. So that includes the elliptic vibration over both a smooth space like P4 and a singular base like this weighted projective space. And for a number of examples, we checked the 2D gravitational anomaly cancellation for them, either without a gauge group or with a non-histographic gauge group. The subclass where we checked an anomaly are actually okay. So I'm gonna talk about the 2D gravitational anomaly cancellation in more detail now. So in 2 dimensions, the anomaly polynomial is a 4-form with I4. So that's kind of similar to the 6 dimensions. We also have a Green-Schwarz mechanism. Although that can be used to cancel the gauge anomaly, and there's still a pure gravitational anomaly, and that has to be cancelled by itself. So this was already studied by the previous papers like Craig, Sakura, Timo, and Xu. And for the gravitational anomaly, the cancellation, well, the contribution has the following 4 parts. The first one comes from the bulk moduli field that includes a vector multiplate, a chiral multiplate, a Fermi multiplate, and tensor multiplate. So that are easily read off as Hodge numbers of either x5 or b4. The only thing you need to keep in mind is that the chiral multiplate has a +1 contribution to the A moduli, while the others has a negative contribution. So after we combine them, the total contribution can be written like as a linear combination of some topological numbers. So here tau is a Hertzsprung signature of the base fourfold B4. And chi1 is the first Euler characteristic. And besides that, the second contribution, A universal, just come from the universal single gravity multiplate, and that's just equal to 24 in all the cases. And that's okay. Then the third contribution come from the A37, come from the super multiplate in the D3, D7 brane sector. So this is because, this is actually a new thing in the 2D theory. So because of the requirement of the tidal cancellation, so there are forced D3 branes wrapping a particular 2 cycle on the base fourfold. And the 2 cycle is computed as the put forward of some like a complex A form over on the X5 to the base B4. So on this D3 brane, there are various multiplates that includes the chiral multiplate and Fermi multiplate, which has a certain multiplicity. After sum of the contributions, we get this A37. Finally, the fourth contribution is from the D7 sector, and that related to the the matter spectrum in the 2D theory. So for the cases we are looking at, a non-hexagonal gauge group, actually all the quantities are geometric. So the examples we take are the generic vibration over a particular type of base fourfold that's called a generalized Herzberg fourfold, as analogous to the Herzberg surfaces Fn in the 60 case. So here I just listed all the toric rays, and as you can see, there's a single toric divisor that support a non-hexagonal gauge group. So we directly computed the anomic cancellation for these cases with various non-hexagonal gauge groups that include SU3, SO8, E6, and E8, and we found that the gravitational anomaly is always perfectly cancelled independent of the G4 flux choice. So in fact, for any vertical flux G4 that satisfies transversality condition and doesn't break the gauge group, so those numbers are always holds. Okay. So those are for the smooth spaces. More interestingly, we also look at the singular base, where we consider the B4 to be a weighted projective space with a C4 over Zn orbital singularity. In this case, although we have some fractional self-intersection number, the crucial topological numbers, the Herzberg signature and Chi1 are still well defined following this mathematical paper on the combinatoric approach to toric singular varieties. And after we plug this in, we found that the gravitational anomaly is almost cancelled up to some very small new contribution that's conjectured from a base singularity. So we computed this new contribution for various different Zn orbifolds. And as you can see, the numbers are different. So in the future, when we wonder what the physical origin of this local contribution, maybe that's from some 2D 0,2 ICFT sector. Okay, so that's conclude my talk about the Calabi-Yau threefold, fourfold, and fivefold with largest h11, and also the 2D F3. Thanks.
All right, thank you, Yinan, for the very nice talk. Let's all thank Yinan with our clap emojis. Our first question is from Fabian.
Hey, Yinan, thanks for the talk. I have two questions. So the first one is, has anybody ever tried to take, let's say, the Calabi-Yau fivefold, or sorry, the Calabi-Yau fourfold polytope that lead to the largest h11 and construct F partitions in there such that you get a Calabi-Yau threefold? It seems like if you could define the hypersurfaces such that few points project to the facets, then you might be able to get a larger number of h11 in these cases.
You mean the polytope in the Calabi-Yau fourfold?
Yeah, just start with any, let's say start with a 5D or 60 reflective polytope and find F partitions such that you get a threefold. And then would you get something that's larger than 491? Because
that's
non-trivially.
Yeah, that's a nice question. I kind of expect that you will now exceed the 491. I don't think anybody has actually tried.
Okay. So why do you expect it? What's your intuition?
I think the first thing is I'm not sure whether the resulting thing can be like a good Calabi-Yau satisfied property.
Yeah, of course, you need to check that an F partition exists. Right? Maybe there doesn't even exist one. I don't know.
Yeah, but well, of course, I don't know about actual detail, but that's a nice thing to try, of course. Yeah.
Okay, and then I have a second quick question, if I may.
Yeah.
It's kind of naive, and I should know this, but I don't. So what fixes the topological twist when you do the compactification to compute the anomalies?
2D anomalies.
Yeah.
You mean the so like some of them are just come from the the 1D M3 picture and uplift to the 2D. So you mean the 7 branes or?
Yeah, for example. So don't I have the freedom to perform a topological twist there?
That's kind of depend on the normal bundle. Like for 7 branches, depend on the normal bundle.
Yes.
Surface is threefolds that support the gauge group.
Okay.
Because that appears in this multiplicity formula.
Mm-hmm. Okay. Thank you.
And we have time for one more question/comment from Wadi.
Hi, very nice talk, Yinan. Interesting stuff. I just have a quick comment in response to Fabian's question, and then a question. The comment is, I think one reason not to expect H11 to be bigger than 491 for the threefold is we know you can prove that H21 cannot be larger than 491 for an elliptic threefold. That you can prove rigorously. And we think that at large H11 and large H21, all Calabi-Yaus are elliptic. So if you found something with H11 bigger than 491, it would have to be mirror to something non-elliptic, which would be a surprise. The question is, you drew this nice picture of the starting point for your fourfold for the base of the fivefold, and it looked like a hypercube. Is it actually a hypercube, or are there some distance, some distances on those, so that those V's are not just unit vectors or something like in the threefold case you have a
Yeah. So I didn't list the coordinates, but it's a very long shaped thing. It's not a cube at all.
Okay, but it's but it's got the same number of faces as like in your threefold base. You had something which looked like a cube, but it was very distorted, right?
Yeah.
This looks like a hypercube, but it's very distorted. So that
very distorted.
Okay, cool. Thanks. Do you have any insight into why that always seems to happen?
So that's just come from the so first you need to I think P231 vibration structure is universal, and then you need to single out the ones with a E8, and I think this kind of structure is just universal, although we didn't prove for the generic XD.
Okay, cool. And just a quick comment on responding to Fabian's comment in the chat. Yeah, I think the large H11 being elliptic applies for all Calabi-Yaus regardless of construction. They found it also in the CCs. Laura Anderson, James Gray, collaborators found that in the CC case as well. Thanks anyway, nice talk.
Okay, in the interest of time, I think we better stop here. Thanks, Yinan, again for the very nice talk.